Rob. Something coming. Yeah.
You just looked at me like you shrugged your shoulders like.
Yeah. I just wanted to make sure I was in the right room.
Oh, okay.
Because when I left, there was nobody there.
Oh.
Just kidding. There was this kind of part. I didn't see Dropbox and details, so I'm just probably good. So this is abstract. I tweaked a little bit, and it's like 1,065 characters.
You don't want to send it by email so that all of us can see?
I would say after this version, I'm gonna send it to everybody.
Okay.
I don't want to send like very rough abstracts to that $1,000,000 every time.
Okay. Good. Okay.
Yeah, that's 1,065 characters.
I think the answer to the question, did we want to write another lab report for the students was no.
Yeah,
Yeah.
I was trying to weigh that against like grading another set of lab reports. So I was okay with the initial investment.
Yeah.
If we still have to write, we still have to grade something they wrote.
That's true.
It's just that then we have to go to the added bonus of writing something for them. I do like the way they're doing it next semester.
Oh, yes.
Yes, with the limiting.
What are the changes coming? This is for the lab?
Next semester for the lab, they're limiting the sections to 8 students. And so that we're only going to progress one lab per week. And smaller sections of students, so we're not.
What's happening this semester?
This semester we're doubling and sometimes tripling.
So there's 3 labs running simultaneously in one room. I see.
And we don't necessarily have enough equipment to do that. And
Are you teaching 203? Are you teaching 200?
Yeah, 253.
253? Yeah. Yeah, I ran into that problem last semester. I had a big class, and I think there were only like 2 or 3 Wheatstone Bridge apparatus things. So it was really difficult to, because there was like 3 things, but each group was like 7 people or so. And then 1 or 2 people would do the whole lab, and then everybody else would just kind of watch. Which kind of sucks, I guess. So, but I talked to Dr. Talapatra, and he was mentioning what they're doing this semester is trying to figure out what they need more of and how to better accommodate for that sort of stuff. So.
quit relying on Pasco so much. That's one of my suggestions. Their equipment is not reliable, not the
Pasco.
The more computer collection that you get, the more error.
Yeah.
I still use photo gates and
Yeah. I am also a fan of old equipment, not just because they go wrong. I think that if you use a computer, how do you do error analysis? The computer spits out an error. Like, for example, if you ask someone to plot distance versus time, that fitting that slope is not straightforward. And computer just plots one and then gives an error bar on that. So I feel error bar is a big thing in physics labs, and computers take away that to a certain extent. It's hard to estimate that. But yeah, live with what we have is. So I'm noticing, was there a place to submit the extra credit today?
Extra credit?
Yeah, yes, right? Was there anything that there where there was no place to submit something?
For homework 6, because the due date was already passed.
No, homework 6, I submitted homework 6 yesterday.
Really?
Yeah.
Okay.
Oh. Maybe it said that it is due date is passed, but I postponed the
Yeah.
availability
Homework-
date for a
Homework 4
longer
and
period.
homework 5, the submission portal is closed,
Yeah,
so they can
but it
submit
wasn't
homework
closed
4
for
and
six.
homework 5.
So there is no way of knowing for the student, like how did you know that you could submit and how could Moses not know that?
when I
You
go
just
to,
have to
when
check,
I
I
went to
guess.
assignments, I scrolled down to homework 6, it didn't, I don't know, maybe I.
Usually, usually when it's available, you see hyperlink there. If you click, it takes you to a different page
Yeah.
where you can submit. And if it is not available, it says closed.
Yeah, right.
So looking for the hyperlink.
I just missed it. I'm sure I just missed it.
actually, I tried to submit online last night and it might have just been a computer issue because it wouldn't let me submit the extra credit.
Oh, interesting.
I clicked on it, it did not bring up the
Okay.
window for uploading a file.
Sure.
Tell them again, so this is for this course?
For this class, for the extra
Yes.
credit for today.
I think that is a D2L thing that's happened to me.
I think,
Yeah, it could be just D2L's not acting right.
See.
I think 2 weeks back, I was not even able to log in.
So how often has this happened with you?
This is the first time it actually has happened.
Yeah, it does currently say that the homework, because I remember for some of the other homeworks they didn't close until after, but the homework 5 and 6 that I guess were supposed to be turned in by Friday, both are closed. And then you can't actually click on the link to still submit late,
I see.
which I think in the other class that you could.
No, it depends on the amount of time I give. I mean, I think at that time, whenever I'm assigning, it's my mood or whatever I think about it. It's not that end date is not a very strict pattern, but I do have a strict pattern for the due date that it is before the class. And these days, maybe it is 11:59 p.m. But the leverage that I give for how long it is available, I don't know what I decide based on. Yeah, it's just random. And I thought I was giving 1 week extra for this one, but I don't remember it exactly. But I try to put that down on my sheet here, and maybe the extra credit 2 days. I haven't yet opened it, so it may not be available in the next hour. But if you're planning to do that, I know sometimes some of you guys really do it within an hour. So it should be available within the next, like soon afterwards, I leave, I'll try to get that done. So. Reading is piling up. Okay, so. So if I understand correct, that's a homework 7. Not sure what Is this readable?
We have to change it.
Change the time.
Can you change the view camera? It's facing towards us.
Oh, yeah. Thank you. Oh, Alia is also there. The relatively small homework. First one, actually, if I remember right, that's not to be submitted. That's mostly done in the class, sort of, or maybe one of the examples was done in the class. So it's very straightforward. But if you want to understand the second problem, first problem is the details. Second problem is just the question. So you don't have to submit the first problem. Okay. And there's a midterm. Okay.
I think it's the 19th.
Okay, so we did a problem on, or a problem involving legendary polynomials, and I thought I would do one more problem today, which uses legendary polynomials in a certain way. If you remember, the style of approach was slightly different on Friday. We were not really solving integrals. Instead, we were using the property of orthogonality of legendary polynomials to get the solutions. And that's what we want to explore today again, how we can use the idea of legendary polynomials to do certain problems. So let's think of a simple scenario. Let's say a charged ring, uniformly charged, right? Uniformly charged. And let's try to solve that, right? So this is the ring. So infinitely thin ring, that's the idea. That's positively charged, let's say. And charge per unit length. And let's say this is our axis. The symmetry axis now there. You can choose this to be our Z. And now the, oh yeah.
It seems like maybe that pin is, or maybe the
Then it's not good.
yeah, maybe not. It's hard to see some of the fainter portions on here. I can still see it. Like the dotted line you just made is like very faint.
Begin with this. Better?
Oh yes, much better.
Okay, so remember vector R we use for observer point, observer, and R prime is for source. So R prime is everywhere on this ring, right? That's where the source is, and we would like to find the electric potential due to this. Some of these problems.
I think they didn't make the prime sign.
Right. Oh, thank you. Thank you. So R prime is a source, and that's on the ring. We do these kind of problems in when we do electrodynamics, or sorry, electrostatics in undergraduate. Right. So this is observation point. Let's say somewhere here. That's your R, and let's say that's your angle theta. So R theta phi, right? So this is the length, is the magnitude is R theta, and it will be symmetric with respect to phi. Wherever you are on phi, it has to be the same, because if it is uniformly charged by symmetry, it must be the same. So there shouldn't be any phi dependence. So let's try to do this problem. So we have the standard relation R, right? The electric potential here, let me specify that this is R, theta, and phi, right? And there will be no phi dependence because of the symmetry. And that's equal to 1 over 4 pi epsilon naught. And use superposition principle for a point charge. This is R minus R prime. Right? Charge over that is for a point charge, but I have a lot of point charges. I have to integrate over all of them. So that's given by the cube R prime. So that's a summation over, instead of charge, it is charge density. Right? And it is charge per unit volume, volume cancels. There's a charge remaining there. And that's how we want it. So we want the charge density. Right? So that's a point. So what's the charge density for a ring? The charge density for a ring, and I would like it in terms of spherical polar coordinates.
So I have a question really quick.
Yes, go ahead.
Can you explain to me why for a ring you wouldn't have the charge density of R minus R prime still? Like, why is it just a charge density of R prime?
Charge density, you mean this is not R minus R prime, you're saying?
Yeah, shouldn't it be R minus R prime?
No, right? Okay. For example, let's say.
No, for like a point charge where you're not looking from another perspective, it's just the prime, but.
Yeah, so let's see. Okay. So your question is why R minus R. Okay. So let's do it for a ring, right? Pretty convinced why is it not R minus R prime? Again, ask me, why do you expect it to be R minus R prime?
I guess that's just the way I've always seen it. That's my main reason, but R prime, since that's the.
If it is R, okay, how about this? Yeah, if it is R minus R prime, right? You would like this to be R minus R prime. So tell me, what is R and what is R prime? So I'm trying to understand myself, okay? So I don't have a clear answer. So what is R and what is R prime?
Yeah, so I would actually, I guess, maybe I'm thinking backwards from what you have, where R would be where the charge is, and R prime would be where you're looking.
Yeah, but the charge density does not depend on where you're looking, right? Charge density is charge density. It doesn't care whether I'm looking at it or not.
I'm just thinking in terms of R itself, not specifically the charge density. I don't want to keep you here too long, but I guess that's the way that I've seen it. Maybe it's backwards from the way that you have R prime. Maybe I'm just thinking about it incorrectly.
Probably I would guess that you haven't seen it that way, but I'm wondering why I'm confused actually, why you're, okay, so again, let's try. Okay. How about this for a sphere, right? What's a charge density for a sphere? Yeah, let me just not even write anything. What's the charge density for a sphere? Right? Or maybe, I think I know what you might be confused with. For a point charge, right? Maybe this is what is bothering you. Point charge is rho of R. This is not neither observer, neither you want this. So there's a double prime, right? None of them is equal to Q times delta function of R double prime minus wherever the position of the charge is. Right? That's how you would write that. Correct? Agreed?
Yeah, yeah.
And now if I want, there are many of the charges, and I'll integrate this. So let's say there is a bunch of them. So, for example, for a ring, right? Rho for a ring would be equal to, I have to integrate over some RQ, right? So let's get dq, RQ actually, times Q times delta of R prime minus RQ. And then I have to specify some function here, f of RQ, which tells me how much charge is there at each position of RQ, wherever the charges are. Agree?
Yeah, I think you actually just completely answered my question.
Right. And once I do this integral, I am left out only with R double prime.
Yeah.
Agree? So
I was thinking, I realized what I was thinking is rho R prime multiplied by R minus R prime.
Oh.
I guess that's what I had in my head. But
yeah,
I was, for whatever reason, I was thinking inside the charge density, but I was mistaken.
okay.
You answered my question with that because I was thinking about the delta, I think.
Okay, good. So I can stop this?
Yeah.
I don't know.
Yeah.
Proceed. Okay. I had to think a lot how to proceed there. What is that function? Okay, better. So, okay, so now tell me, since I know this, what's the charge density for a ring? So it exists only on a line right there. So let's say the total charge is Q also, if you want. Oh yeah, it needs to give some numbers, right, or parameters. This is the radius A, total charge is Q. Yeah, can we charge density solutions?
Total charge over the circumference.
Yeah, so total charge over the circumference, the 2 pi A, and
The delta function.
a delta function of
Rho minus 8.
rho. I wanted spherical polar abundance. R, you mean to say? R minus
I thought it was cylindrical, so.
R.
Prime minus A.
Or R prime minus A, yeah, reasonable. R prime minus A. That's a sphere, no?
Yes.
It's not a ring yet.
Another one with theta.
Another one with theta. Theta
Minus pi over 2.
minus pi. This is theta prime now. Notice this is not theta. That's not that. Reasonable?
Wait, sorry, why is it R prime and theta prime?
Oh, because I chose this to be one. Like I'm saying, this is for source and that's for observer. This is observer. Charge density does not depend on this point. So I need another variable. I picked another variable to be R prime.
Yeah.
At this stage, it doesn't matter. I can write R, but I have been trying to be consistent as to what is eventually what is going to become the source of writing R prime.
I see.
That's just to avoid confusion, visual confusion. There cannot be any error. Is that reasonable? Want to check on that? Is that right? Is that correct? I said it's wrong. It's dimensionally wrong.
Should it be the magnitude of R prime minus A?
R prime, this is spherical polar coordinate. It is never negative, right? So that's okay.
Okay.
How about we write delta R prime minus 8 over R?
Huh? Yeah.
I think that makes much more sense.
Yeah. So usually what happens is that whenever you write a delta function, so remember your scale factors. Right? So what's your variables? Yeah. So this is U minus U1 comes with H1. Right? Delta of U minus U2. Remember if you're working in arbitrary coordinates, this is H2, and these are scale factors. Right? So for R, remember, how do you know the scale factors, by the way? Look at the metric, any distance, this will be dr squared plus r squared d theta squared plus r squared sine square theta d phi squared. Right? So that's your scale factor with r. This is the scale factor with theta, only the without the square root of that. So we need the scale factor for r prime, that is just 1. There is no scale factor in there. For theta prime, as Avinash was pointing out, so now theta prime has a r associated with it. So it is r prime. But then r prime is actually a. And wherever this survives, that's r prime is equal to, so you can also replace it with a if you want. Right? And then dimension lengths, okay, charge 2 lengths in the denominator and delta function corresponds to 1 over the length. Right? Remember the dimensions of delta function is 1 over whatever its argument is. Right? Because it's 1 over the volume, right? It goes to infinity. Right? Yeah, extra credit. Deduce the dimension of delta function. And this also, you guys have all heard of Fourier transform, right? Here or there, like you might not have too much fluency in it. But let's say f of Fourier transform, let's say f of x or f of time, right? Then you have a frequency interpretation. This is d omega over q pi e raised to minus I omega t and f tilde of omega, right? Minus. That's Fourier transformation. So this will be called the Fourier transform of this function. This is time dependent. This is frequency dependent. If you want, these are unit vectors in some basis, some function basis. These are unit vectors, and these are the components of those unit vectors under the function space. Similarly, in legendary polynomials, we get asked this. Now, tell me, what is, suppose the dimension of f is, what should I say, some physical quantity. What is the dimension of f tilde in terms of f?
F over f times time.
F times
over frequency.
Yeah. So what? Yeah, that's correct actually. Notice that it is not the same. What I'm trying to point out is that the Fourier transforms don't have the same dimensions. It's the same thing with delta function. Like notice if you were to do dimension of f is equal to, there is this integral d omega. Omega has a dimension. So this is dimension of omega. Exponential doesn't have any dimensions. Whatever it is, it will throw in a number. And that's dimension of tilde. It's not the same dimension. So often that's a source of confusion. Wherever you see electric field or anything, you have to first make sure, is it in time or is it in frequency space? They do not have the same dimension. Same thing, that's sort of related to the delta function. Delta function sort of contributes to that. Okay, so that's our charge density. Okay, so we can as well say that this is equal to q over 2 pi a square prime a minus pi by 2. There is one point. Rob pointed out that this is q over 2 pi a, so that was very nice of him that it is charge per unit length. How did we know that? How are we so sure that this is correct actually? What was the motivation there? Like, why should that be charged per unit length? Especially if it was a non-trivial geometry. So then what you do is that put that as a constant there. We don't know, but we do know that the total charge has to be Q. So do the integral total charge, and it should come out. So for example, if you had left this alone, so this was, in that sense, even this you could have left it alone, right? We don't know what that R prime is. If you had just picked up these two delta functions and left everything else as a constant, it will come out as Q over 2 pi A squared. For example, if you had run, this is rho of R prime is equal to some constant C times delta of R prime minus A, theta prime minus pi by 2. And what we do know is that if I were to integrate over all space with respect to that ring, that's charge Q. R prime, rho of R prime. I'm integrating everywhere and asking wherever there's a charge, I want to collect that. And that's equal to C you're saying that that doesn't depend on R prime and theta prime. So that's C. This is 0 to infinity R prime square, ER prime, 0 to pi sine theta prime, d theta prime, and 0 to 2 pi d phi prime, and delta function of R prime minus A, delta function of theta prime minus pi by 2. And then do the two integrals are immediate. Whenever there is a delta function, that's the simplest integral, just replace everything with the quantity in there. So C R prime square gets replaced with A square. Sine theta prime gets replaced with pi by 2. Sine pi by 2 is 1. So it's sine of pi by 2, let's say. And d phi, there is no phi prime integral. So it's 2 pi. Right? So we do get Q is equal to C times 2 pi A squared, and that's your C is Q over 2 pi A squared. Right? So that's typically how you go. But if you have experience, then you know that that's how it should work out. So that's good. Okay, so now we have the charge density. Electric potential should be straightforward. Plug it in, complete the integral. That should be straightforward. By the way, what is the answer for the charge electric potential due to a charged ring? From your earlier courses?
I don't remember on top of my head. I have to calculate.
While I go a few steps, you guys try to remember. Okay. Okay, so that's 4 pi epsilon naught. We do this now, we just plug this in and substitute it in, right? So this is 0 to infinity R prime square. This is over all sources, right? 0 to pi sine theta prime, d theta prime. 0 to 2 pi d phi prime. And I'm writing it as delta functions. Typically, you can immediately write it, right? Usually, when we're doing undergraduate physics, we don't write all these delta functions. We just visually say that, oh, this is a distance. We use the idea of calculus, right? All these small elements are contributing. That's how we used to see. This just is a more formal way of doing it. Okay, so this is Q over 2 pi A square, R prime minus A, delta function of theta prime, is replaced by pi by 2. And what is R minus R prime in spherical coordinates? Distance between 2 points in spherical coordinates. So this is R theta phi. And this is R prime theta prime phi prime. What's that distance?
We have that on z-axis is just going to be r squared plus r prime squared minus r prime cosine theta prime.
Why is it on the z-axis? What is on the z-axis? Our observer is here. Right? And my source is somewhere here, anywhere on the ring. Correct? So it is not, it doesn't simplify. Correct? So this distance actually is, remember, r minus, I think what Avinash is saying is this is equal to square root of the square of this dot product. So let me write that. R prime dotted with r minus prime, square root of that, and this is r square plus r prime square minus of dot product of two r and r prime, which is r prime times this is not straightforward. So this is equal to sine theta. We did do this last time, right? Structure for this plus so cosine of phi minus phi prime plus cosine of theta prime. Right? And the whole thing underneath the square. Oops. Okay. So it doesn't, so neither of them is on the axis, but we do know that theta prime actually is on the xy plane. So that's a simplicity there. It's not the observer that is on the z-axis, but now the source is on the xy plane. So that leads to some simplification, but let's do that in two, because this delta function is supposed to do that for us. So let's do that in 2 steps.
So I have a quick question really quick.
Yes, go ahead.
The first r squared term,
Uh-huh.
if you were to write it in matrix form, it would be 0, 0, z squared? Because we're on the z?
No, we are not on the z. This is the observer point. That's just as axis.
Okay.
It's just a reference line.
Okay.
Observer is here.
Okay.
Right? So if you put it on the z-axis, yeah, we'll talk about that.
Okay.
Yeah. Meanwhile, you guys are supposed to give me the answer for this undergraduate course, right? Okay, so I can do the r prime and theta prime. That's equal to 1 over 4 pi epsilon naught. Q over 2 pi square comes out. R prime gets replaced with A, so that's A square. Theta prime gets replaced with pi by 2, same thing that we did a little earlier, so that's sine of pi by 2. And everywhere I see r prime and theta prime here, r prime gets replaced with A, theta prime gets replaced with pi by 2. But d phi prime integral stays 0 to 2 pi d phi prime. And these two integrals are gone. So it's 1 over r square plus r prime is A square now, minus 2 r A. And when theta prime is pi by 2, this survives, which is 1, but this is 0. Cosine of pi by 2 is 0. The second term goes away. It's the opposite of what happened on Friday. Right? So this is Christian?
I was just going to say it looks like elliptical integral.
Yes, that's very good. Yeah. That's very good. Just hoping that you something. Good. So, and this integral cannot be done. You never saw this in undergraduate physics. A charged ring, but you did see a charged ring, right? Electric potential charged ring. What was the simplification? It was always on the z-axis. We never go beyond that. Never go beyond the z-axis. On the z-axis, it's very straightforward. On the z-axis, what's the simplification? Theta is 0. The moment this becomes 0, there is no phi prime dependence after that. This is 2 pi r square minus a, you know the answer immediately. Right, so let's do that. So first let me write one more line, and then I will write the answer for theta equal to 0 on the z-axis. 4 pi epsilon naught, a square cancel, sine pi by is 1, so it is q over 2 pi. And I can also substitute, notice it should not depend on the phi, right? Where do you see that it seems like it depends on phi here? Does it depend on the phi? And why doesn't it depend on the phi? What about this phi? Right? So the point is you can substitute, right? Substitute phi prime minus phi as phi double prime. And when you do that, d phi prime is equal to d phi double prime. And your limits of integral will go from 0 minus phi to 2 pi minus phi. But who cares whether it shifts as far as I go all over the circle? It's a summation. Whether I start from 0 or phi, it shouldn't matter. Is that argument clear? Right, so that is it. So I'm not going to write that. I'm just going to skip that phi. So what the point is, if you do this, my limits of integral will go from, when phi prime is 0, it is 0 minus phi. And this is 2 pi minus phi. And inside of the integral, this will become d phi double prime of a function of just phi prime. Sorry, phi double prime. But the point is, this is summation. Who cares whether I start the summation from 1 to 10 or I start from 3 to 10 and then come back and add 0, 1, 2. Summation is, it doesn't depend on the order as far as it's finite sum. If it is infinite sum, then there are problems associated with that. So this is the same as 0 to 2 pi again. As far as I cover everything, that's good, you know. This is double prime. Any questions on that? So using that, I immediately say that this is equal to 0 to 2 pi, phi prime, and 1 over square plus a square minus 2, let's say a r sine theta times cosine of phi prime. And as I said, this integral doesn't have a, it cannot be done using simple functions, but it can be done using elliptic functions. Or we will do using legendary polynomials. But before that, I said I will point out what is the answer for phi of r theta equal to 0, right? Phi of r theta equal to 0, and then after that phi doesn't matter, right? There's no phi dependence. That's simple. This is 1 over 4 pi epsilon naught, q over 2 pi, 0 to 2 pi, d phi prime, and this becomes theta, so that's 1 over r square plus a square. In fact, r square now is z square. Right? When it's on the axis, r is the same as z. This doesn't depend on phi, so that's 2 pi, 2 pi, 2 pi cancels, and this is equal to 1 over 4 pi epsilon naught, q divided by z square plus a square, right? Dimensionally, it should be charge per unit length. It is charge per unit length with the 4 pi epsilon. So I think that's the answer for the electric potential on the axis of a charged ring. Okay, that's good. So I have half and half. So by the way, just I should, yeah, it's not necessary for this. I don't have to go through this, but it is good to know that this has an answer in terms of another special function. We are doing legendary polynomials. This can be written in terms of what is called elliptic functions. So I'll not go through the details, but I will write down the answer for you guys. Switch. Okay, so these are called complete elliptic integrals. Usually special functions always comes in pairs. And this is it's called the first kind and the second kind. So it's the first kind, which is K. So this is capital K. And it's a function of small k. It's reasonably standard terminology. So that's capital K, that's a function, and its variable is called small k. When it is in typography, then it comes out much more clear. In my way of writing, probably looks the same k. So that's equal to 0 to pi by 2 psi 1 over 1 minus k squared sine squared psi. That roughly gives you the idea. Notice that there's a phi prime, there's a cosine phi prime here, right? We use the trigonometric relation of cosine phi in terms of half angles. You get a sine square there. And you can pull out whatever is a constant in front and whatever is there in front of it, that you define it as k squared. That's the idea. But notice this is 0 to 2 pi, so you have to do little work on converting that 0 to 2 pi to 0 to pi by 2. But it's simple, straightforward. But let me not go through that. It will be a distraction at this point. In terms of this, I can tell you that this integral, and there is a second kind, by the way. Just for your information, we'll do this more when we are doing magnetism. We'll actually explore the whole thing. What's the circumference of a circle? By the way, this is just a definition again. Circumference of a circle should be straightforward, 2 pi a here, right? What's the circumference of an ellipse?
Maybe the check function again.
Yeah, most probably you've never seen it. Okay. It doesn't have a simple form. It is written in terms of elliptic function. That's why it's called elliptic integral. If you were to evaluate the circumference of an ellipse, the integral that you get cannot be done. That's that integral. So that's how the name comes up the first time. Probably. So circumference of an ellipse is not straightforward. You probably didn't see it earlier. If you're not seeing elliptic integrals, you're probably not see it. Second kind is actually, that's why I was right. Second kind is what involves the circumference of an ellipse. So this is 0 to pi by 2 d psi, and this is started in the numerator.
I have a question.
Yes, yes.
Can an ellipse always be pulled into like a circle, like into a perfect circle shape?
What's the question again? Repeat your question.
Say you have an ellipse.
Mm-hmm.
Can you stretch an ellipse and make it a circle?
Stretch, yes. Topology, yes. If you stretch it, yes. If you're allowed to stretch it, yes. Yes, that's correct. So that transformation probably, so in that sense, you'll be able to find a transformation that takes you to a circle. Yes, yes. So I think the idea would be like you want a mapping typically, right? So this is a circle and ellipse is usually like this, like maybe, right? And then this is the mapping, right? Like if you know the coordinate of this and if you know the coordinate of that, then there is a mapping from this coordinate to that coordinate. And that's your transformation that takes you from one to the other. And there's a one-to-one mapping there, including the north and south pole. But from a circle to a line, there is a small problem that one point doesn't get. Have you guys heard this? Like if you were to try to map a circle onto a line, there's a problem now. So that is, if you were to do again the same idea, that this point goes to that point, or not this. I want to start from here. So this point goes to this point. So using coordinate geometry, we can get that transformation. But you can keep doing that, but this point doesn't go anywhere, right? It goes all the way to infinity, but infinity is not part of our system. So you lose that information. So in that sense, a circle cannot be mapped onto a line. So, but circle, I would think, can be mapped onto a ellipse. So yeah, that must be that transformation must be this, right? There must be a way to show that using that transformation. You can do that, yeah. So that's how you play around with it. But yeah, don't ask me to do that now. It's just a thought. I don't know the details. Okay. So in terms of this, I will just write down the answer. We don't want that at this point. We are going to do another route. It's 0 to, sorry, we were doing 0 to 2 pi, right? 0 to 2 pi and d phi prime. R square plus a square minus 2ar sine theta and cosine of phi prime. This integral comes out to be equal to 4 over 2a rho and yeah, so there's a new variable I come up with, k, and small k, but then I have to tell you what is k, right? And k is this in here. That is 4a r sine theta divided by r square. This is k square, so square root of this, right? R square plus a square plus, not minus, plus. This is a minus here, but that's actually a plus. 2ar sine theta. Okay. So if you know this function, you put in these variables here. If you understand this function very well, you know the electric potential everywhere in that sense. But it turns out that, see, for example, if you have let's say, trigonometry involves sine theta cosine theta, like there are trigonometric functions, and let us say, what is another set of functions? Can you guys tell me another set of functions that are not trigonometric?
What do you mean?
Yeah, what do I mean? Let's say trigonometric functions are available to us, but that's also a function, right? That's a series basically, sine theta is. But we know a lot about sine theta cosine theta. Like there are lots of identities, very well studied function. Let's say there is another function. I cannot think of any simple ones. Let's say Legendre polynomials. Right? Even though you have an answer in closed form in terms of Legendre polynomials, you might not like it very much because Legendre polynomial is not as well studied as sine theta. So you might be ready to pay a price that I don't want an exact solution. I want a series solution, but give it to me in sine theta cosine theta because I can manipulate more with trigonometric functions than with Legendre polynomials. Right? So sometimes you pay a price that instead of exact, you go to a series and then you do it in known functions. Yes.
Under the 4, under that square root, is that the?
Rho. What was that? So that's just our sine theta. Rho is basically, if you notice in this r sine theta, there is this distance here, right? If I were to go further out, right? So that distance is the cylindrical polar coordinates rho. So I remember it in terms of that, but then I forgot. Like this is usually written as 2A row, 4A row, but I forgot to convert that. Okay, so yeah, so the point is, so in that spirit, whatever I said in trigonometric functions and legendary polynomials, in that spirit, elliptic integrals, even though they are older than legendary polynomials, they are less, so we know less identities about elliptic integrals than legendary. Legendary is much more easier to work with, or there are much more identities available. So at the price of, this is an exact solution, but say, oh, let's work with legendary polynomials. Okay, so we want the solution in legendary polynomials. It won't be so compact as this, but then it will be more powerful because we know the legendary polynomials better. Once you have experience with it, it's better than elliptic. So having done that, so this is the exact solution. We proceed and go back and say that I want the function f of r theta in terms of legendary polynomials. So let's say I don't know this function, right? So I say this problem. I mean, since this is all dimensionally, this can be wrong. So I say this is some function of r, and the theta part I don't know. Whatever it is, so let's say this is f of theta. F of theta. Or this can also depend on r theta, right? So this is just I pulled out the dimension with some potential times this. So this is not necessary, but and if I know a function in terms of angular functions, I can express it in terms of legendary polynomials, right? So this is PL cosine theta. So remember here, you can Fourier series is in terms of sine theta cosine theta, but now this is a series in legendary polynomial. I want the coefficient of the first one, second one, third one, and so on. But I don't know that. That's my goal. I'll let them be L. And they will be dependent on R actually. R. And this is L equal to 0 to infinity. Is that clear, this expansion? Right. Any function can be expanded in terms of sine theta, cosine theta. That's Fourier series. Any function in theta, right, angular function, can be expanded in terms of legendary polynomials. This is legendary expansion if you want. I don't think it's called that, but you can. Any function can be expanded. And this coefficients, I would like to know, it depends on this function. If I know this functions, I know this. I know the solution immediately. Right, that's the goal. So let me write that. So I would like to know my AL. L equal to 0 to infinity AL of R times PR sine theta PL. Okay. Notice this could have been my first step. I mean, I did that to construct and motivate the problem, give you the feel for the problem, but that could have been my first step. I didn't have to go through all that, right? And the goal is to find AL. And now look, notice how simple it's going to be. I need to find my AL. So I need to, usually whenever you have missing coefficient, you look for some known places where I know the function, right? For example, when I was trying to get that C, right? I integrated it and I know the value to be Q, and that gives me my value of C, and then C is C, right? It cannot change after that. Right? Similarly, if I can get this for one point, that's good enough. That fixes my AL. And then I'd say that that's the same thing for everywhere. And I do know the potential at one point, or not only one point, I know the potential on the whole axis. Right? So we will use that to find AL. Right? So let's find phi of R theta. Sorry, R0. I know the answer. Right? So if I can expand that, so first let's do that here. What is f theta equal to 0? 1 over 4 pi epsilon naught. Q of R. Is that strategy clear, by the way? I repeat the strategy. So this is my proposed solution, and it is okay because any function in angle theta can be expanded in terms of legendary polynomial. That leaves me with the question, what is this coefficient? And that coefficient I try to fix by using the fact that I know this left-hand side on the axis when theta is equal to 0. Right? So I go ahead and try to calculate theta equal to 0. So that's equal to 0 to infinity. And this doesn't change. This is what I'm interested in. PL of the sine of 0 is 1. What is PL of 1? Right, actually, we didn't spend too much time on that, but yeah, Avinash? Trying to say that? No. Okay. That's just 1. Turns out that if you were to evaluate, go ahead and do that, but I didn't develop the legendary polynomial. No, I did, right? Did I define my legendary polynomials to a certain extent? Yeah. Yeah, I didn't spend too much time. Yeah, I could have done differential equations, all that. But if you use those definitions, you will see that it's always 1 when theta is equal to 0. So probably it's not very obvious when you look at it. So I cannot ask a question and you will keep knowing. But if you do a little bit of legendary polynomials, you'll realize that that's it. In fact, that's how it's normal. Okay, that's 1. So there's just some of this, correct? But we also know that 5r of 0 is our answer there, right? So it's 1 over 4 pi epsilon naught q over r squared plus a squared. That's nothing but 1 over 4 pi epsilon naught. Let me for a moment say a is less than r, but I can do both ways, right? It is pretty symmetric. Whatever it is as a function of r and a, if I were to swap r and a, it will be the same. So I'll do it for a less than r, but if I were to swap r and a at the end, I will get the opposite solution. Okay, so this is q over r, and this is 1 over 1 plus a over r squared. As of now, this is perfect. There is nothing approximate. But once I write a series, that's allowed only for r tends to r a less than r. So that's my solution. I want to compare these two, right? So I want to write a series, right? I want to expand this out as a series so that I can match 1 to 1. So that's what I'm going to do. This is 1 over 1 plus, let's say, a over r square root, and let's say this is for r or a less than r. That's equal to 1 plus, this power is minus 1 by 2, right? So this is minus 1 by 2 over 1 factorial times a over r squared. The second one is n minus 1, so it's minus 1 by 2, minus 1 by 2, minus 1, 1, so it's minus 3 by 2 divided by 2 factorial a over r squared, and that pattern goes on, right? This is n minus 1, n minus 1, and minus 2, that n is the power of that. That's a binomial expansion. So familiar? 1 plus x raised to n, even when n is not an integer. This is 1 plus n over 1 factorial times x plus n into n minus 1 over 2 factorial times x squared, and so on. So since it's minus 1 by 2, it's minus 3 by 2. And so we want to write it as a series. So this is, let's say, n equal to 0 to infinity. And surely that is a power n factorial, right? So 1 over n factorial, that is a over r raised to 2 times n. So that's 1. I've taken care of this, I've taken care of this, and I have to take care of the numerator now. This is the minus 1 raised to. So this is so the odd powers are contributed,
So,
right? Yes.
so in our extension, the third time should be to the fourth, right?
Yes. Oh, yes. Thank you. Oh, that might have been confusing, but I'll keep that. Sorry, my bad. Yeah. Okay. With me. Okay. Yeah. So, so then I think there is a minus 1 raised to n, I suppose, right? And then there are how many 2's will be there? How many 2's in there? This is 2 raised. This is the second term. There are 2 2's, so there'll be 2 raised to n 2's. And this is since I pulled out the 1, so this is 1, 3, 5, and so on. How far do I go? When in the second term, I go to 3, right? So second term is 2, so it's 2n minus 1. Right? But you got to pick the odd ones. It's not all of them, so it's not a factorial. But I can provide the even number 1 and then write it as a factorial, like standard, right? So n equal to 0 to infinity 1 over n factorial a over r 2 raised to n minus 1 raised to n. So now I'm going to provide the 2, 4, 6 until and the 2n also, so that becomes 2n factorial. And this is 2 raised to 2n, sorry, 2 raised to n. And now that I've provided it down, I'll collect it downstairs, right? In the downstairs, I have 2, 4, so on until 2n. Right? Pull out 2's from each, so there is a factor of 2 raised to n, and there's an n factorial. If that makes sense. Probably you guys have manipulated this kind of stuff sometime before. So this is 2, 4 until 2n is the same as 2 raised to n, 1, 2, 3, n, and then this is n factorial. So, sure. Try to convince yourself of that. And yeah, so that's here summation in n. This is summation in L. This was 1, so forget that. So that's fine. AL. That's my AL. So I figured out what is my AL. Apparently, it's only the even numbers that contribute, right? Even L's that contribute, right? So it's equal to 0 if so 0 is 1, 0 is 0, yeah. So it's 0 when L is odd, right? All right. And yeah, and it is equal to 1 over L factorial A over R to L minus 1 raised to. I think this is correct. And this is 2 raised to 2L, and this is L factorial square. And this is when L is even. So yeah.
Does that 2 to the n, 2 to the n simplify to 2 to the 2L? I think it simplifies to 4 to the L.
2 to the n. So it is, yeah, 4 to the n, right?
Mm-hmm.
But that's the same as 2 raised to 2n. Isn't it? I'll take it. Computer.
N plus 1, yeah, I think so.
Plus 2, 2. Yeah, sometimes it does and sometimes it doesn't. Yeah. Is it always okay to say x raised to a raised to b is x raised to ab. Recently, there was something that
I've always seen like that.
I think it was somewhere recently in your.
Yeah, I think that's true.
Scott?
As long as you don't try to take the A to the B first.
Yeah, I think, yeah, maybe that's what's the point. Yeah, so this is, yeah, maybe that's the point. This is not equal to x raised to a raised to, right? Yeah, that doesn't come. I think that's the point. Yeah, this is correct, but this is not the same. Yeah, the brackets. And that's what I was, yeah, there's some mistake that can happen. Okay, so, okay. So on. So, yeah, that's it. So, what's the electric potential due to a charged ring? Now you know, but it's either you can think of it in terms of elliptic integral, which is a closed form solution, or you can write it as a series, but it's a simpler function, Legendre form. And this is 1 over our factorial. Oh. Since you guys are seeing Legendre polynomials for the first time, this is probably as uninsightful as elliptic integral, but with some experience, you realize that this is actually, there are more identities, basically, there are more identities. That's what eventually decides how much manipulation power you have with that function. So, yeah, so not a straightforward answer, but that's your answer. That's the best you can do. Either that or this. Fair price. So now you're seeing the solution for a charged ring. And I'm 3 minutes early for a change.
So it's not entirely clear to me why AL is 0 for odd L.
How is that the same?
Oh, why should it be the case, you're saying?
Yeah.
Let's see. PL, okay, maybe. It has to, because it is symmetric, I think. Okay, I can plot PL and maybe that will help. I can erase this part, right? Let me plot PL and that will help. So remember the 0 of x, let's say, okay? That's 1. The 1 of x is x itself. It did do this much, right? 3 by 2 x squared minus 1 by 2. Next one is 5 by 2 x cubed minus 3 by 2 x. After that, I don't know. So, so if you had a plot, first of all, x goes only from minus 1 to plus 1. Because cosine theta goes from minus 1 to plus 1. P0 is somewhere here. That's your P0. That's just 1. P1 is positive and negative. Right? You think of the ring now. Right? So theta is equal to, theta goes from, this is theta equal to pi, and this is theta equal to 0. think of your observation point, so maybe you guys do not tell me that. So that's theta, 0, and once you go here, so this point and this point should be the same, I guess, correct? Looks like potential, so it should be symmetric. So theta should be the same as pi minus theta. Right? The potential of theta and pi minus theta should be the same. So, but these actually interchange. The even ones are okay. So they have the symmetries there. So x square goes like this, I think. Okay. And this one goes like this. And so on. Right? So it interchanges signs. So you don't want that. You want that symmetry with respect to this. So the even ones keep that symmetry, the other one does not. And that's what it's a good question. Luckily, I could answer. Yeah. Yeah, I think that's the reason. Unless there is a better answer.
But AL is not in terms of EL, right?
AL is not in terms of EL. Oh, but the point is, this is what decided. That is this, right? The question is, do you want to make this survive or not? Right? If odd survives, then this will start interchange, like serving signs. So you want to kill the odd ones. Killing the odd ones is AL is doing the job, but it is controlled by this. Like it's like saying in Fourier, when you're doing time dependence, sign of some octaves doesn't exist in your music, then you want to kill it. That coefficient should never exist, or you will remove that key from the piano, right? Or keyboard. So think of that as a Fourier transform. But yeah, good question. I think that was
Right. So when you like wrote AL as like, so when you brought in the 0 for L is odd, that was like bringing in physical intuition about the problem.
No, I did not, right? This came out as a series. Remember, this expansion decided that. I did not decide that. This power square decided that. Right? This one was having 1 over 4 pi epsilon naught Q over R, and this was having a sum, right? L equal to 0 to, I wrote it as N, but you can write this as L. N equal to 0 to infinity. There were some coefficients, and then there was A over R raised to 2N.
Okay.
That 2N mattered that. I did not control that. Mathematics did that for me.
So
N equal to 0, then 2, 4.
So should that be in A over R to the L instead of up in the A sub L expression?
Notice that L is even. So what I'm saying is that L takes the value, L is even, right?
So should that be?
I think that's a good question. So if we say L is even, then we are leaving out a lot of numbers.
So this is, you're saying L is all L, right?
Yes.
This takes care of the fact that this is even. I was struggling there. So how do you write this?
So maybe
We'll just take
I
out
can
the
maybe just
2.
put,
But then all this will change, right? How about this?
So
I think I can write this as L, AL,
yeah.
right? And that's L, and this is equal to, this is for AL is equal to this, right? And how do I say that it is 0?
I think if you say that, if you take the like expression like in terms of N, and then write like just L equals 2N for
this, right?
Yeah, so N equals L over 2 for.
Yeah, that's what Avinash was saying, that you can replace this with that. But then I didn't want to write all these in N over 2. You see what I'm saying? This is nice stuff like
I
that.
think,
But I think the only thing.
I think it still makes sense. The only thing that we have to change is L is even when we say
when L is equal to 2n. Is that the point? With n being n positive integer. Is that your point? No, 2n plus 1. Am I good? Fine. This is for L. How do you like this? I'm struggling with that. I shouldn't have gone to the n at all.
No, I think it's okay. I
I think we can just get rid of all that by just saying in the sum down there, L is even.
Only
If we-
the even terms.
If we say there, I don't think we have to go up there.
Yeah. Yeah, actually, that's the correct thing, right? Yeah.
Because
I don't even have to go there. AL is just that.
Right.
Yeah, so AL is
Because-
just this. Yeah, that's
did
all.
did we not say that the coefficient A becomes 0
Yeah.
because of the PL cosine theta thing?
Yes, yes, yes.
So if that term goes to 0, we don't have to worry about
Good.
the coefficient.
I completely agree. So this is what it is. And when you look at here, you notice that, oh, it is, but then it gets contribution, right? For every L.
Oh,
Yeah, there is a contribution for every L.
right. Oh, so that should, I think,
But L equals 1 is 0.
wait, so maybe, do you need like P sub 2L?
Yeah, or what you could do
Yeah.
is everywhere in the AL expression where it says 2L, you just change it to L. And then say that L must be even.
Yeah. Something like that. Yeah, no, that has to be there, right? This 0 has, because this is AL, right? The L can be any number. And L is, yeah. So, yeah, it's not okay. Okay, leave that to me. I'll try to come up with it. Or think about this extra. Yeah, whatever I don't know, you guys do.
Yeah, I think,
What you said about the 2L on the polynomial one,
That would fix it.
I think so.
I think so. So maybe this is true already. Is
Yeah,
that what you guys are saying?
Yeah.
Yeah.
yeah, but it's still, that's still not super satisfying because then you're not getting every basis vector. Like every, in the like Legendre.
Yeah. It's just that it's missing like a 0 in that
Right, but
sense.
you know it's 0. So I think like the best thing is to like do what we're saying of like take L equals, like wherever you see a 2L, write L in that AL.
Yeah, maybe let's do that.
I think that's got it, like,
I think n over 2, that's what you guys are telling me.
yeah.
So summation for n equal to 0 to infinity. So let's see. Yeah, I have to write that down. Minus 1 raised to n over 2n n factorial square. A over r raised to 2n. And then there is 2n factorial over 2 raised to 2n. But yeah, I'm confused. How did you get grasp it from that? I don't know how to pull it from that. Seems like I know the answer, and that's why. or I'm just struggling maybe. Next class, something I think should leave it to me. You guys are convinced what it is supposed to be?
I can
I
work
will not
on it.
sure.
I can work on it.
Yeah, what if we try to build into the sum that n can only be even?
Because this is what we're doing, right? AL in a sense, right?
Yeah.
So what tells me that it is
I
A
see.
over
I think
square rather
everything
than,
is just the same except M
Yeah.
goes to L.
yeah, it's not very obvious then. I'm a little confused.
I think that sum still works if we specify L is even. So
So
if we
can
want to
you
go back,
formulate the question exactly you're trying to
I
figure
think
out?
the point is, like, from this, how do we know that AL is equal, or is it straightforward that this is, seems like it should be true, but it's not. I think it's not. It's not clear that this is actually, sorry, AN. Is this clear? Because one could also argue this is AN R, right? A over. Yeah, right. So can I not also argue that this is equal to? Yeah, if I think of it as, so that there was another argument, right? This is equal to 0 if n is even. Like if I were to substitute 2n is equal to, yeah, so substitute here, I think the mean here is, so substitute, so I, right? So substitute 2n is equal to m. So then when n is equal to 0, m is 0, and so it goes to the next one, right? So this is m equal to 0 to infinity minus 1 raised to n is m over 2, and factorial is m over 2 factorial square, and a over r raised to m now. And 2n is m. Right. And now if I were to compare this and this, it seems like I get different answer. Right?
Right, so I think,
So a m now, which is same. Correct. And now that's what I was trying to say is fine. So how do you, which one is correct?
right, so that, I think that's only valid for even m.
Which one? This one.
Yes. Because otherwise, if you allow m equals 1, then you get an odd term.
but you don't get M equals 1 because M is to M. M cannot be odd. Has
You
to
mean
be
here
there.
or here?
In the bottom, yeah, there.
Here m is
Right.
It is always even.
Yeah. Right, so I think that's the solution, is that m equals to L.
let me also think. I'm not completely satisfied yet. And it's harder. Yeah, okay. Something's, we'll leave it open. But I'll bring it back. If I find a solution, I'll bring it back on Friday. Meanwhile, you guys can also think. Are you guys satisfied? I think you guys are satisfied.
I'm pretty satisfied with that. Maybe I shouldn't, but.
I mean, I'm sure also, right? So, yeah, we
Yeah.
have 2 out of 4, 5, 6 people. Oh, 6, we have 2 people there, 8, I forget. It's harder to link into the computer when there are more people here, otherwise I can look. But it's 15 minutes past. I think I should let you guys go. So think about it and let me know. I will also think about it. Yeah. But good question. Yeah. Thank you. Sorry. That's certain things. Everything I should talk about. Okay, that's all.
Thank you.
Yeah.
Bye-bye.
Here you are. I'll put them on the camera.
Bye, class.